But first, we now go to somebody in the UK who's going to give a presentation about a project in South Africa. Devon, the floor is yours.
Okay, thank you very much, Gerald. I hope you can all hear me, and good day to everyone in attendance. I want to start off by congratulating Dustin on a great presentation. Today, I'm going to talk about a project that I've been associated with for over 12 years, and believe it or not, one that I'm still working on. By way of background, in 2012, I was invited out to South Africa to participate in a series of meetings with an asset owner, the owner of a dam. And the objective of those meetings was to try to convince the asset owner of the merits of using post-tension rock anchors to strengthen their dam, which was going to be raised for increased water supply purposes. Now, after about 2 years of dialogue, the decision was made to use the anchors. And then in 2015, the project actually started. Now, I worked on that project for about 3 years as the lead anchor consultant. And then in 2018, due to procurement challenges and other non-engineering issues, the project was actually stopped for a period of 4 years. And then in January of this year, it started up again and is due to be completed at the latter end of this year. So hence my 12-year association with the project, which is quite unusual. Now, before the project was actually stopped, all 83 of the scheduled rock anchors were actually installed, but only 73 of them were stressed, tested, and locked off. So that means that the current task I have to deal with is to stress, test, and lock off the remaining 10 anchors, and also instrument them with special hydraulic load cells. So that gives you a brief background to where this is all coming from. Now, the reason I've selected this particular case study is that in my 30+ years career, this project in my mind stands out as one of the best examples showing that when an asset owner commits to an adequate program of geotechnical testing prior to the start of the main works, there can be substantial benefits for the project in terms of reduced costs and reduced program time and mitigation of risks. And hopefully this is what I aim to illustrate throughout the presentation. Unlike Dustin, I'm not going to actually quantify any cost savings. I'll do it in a qualitative sense because this is a live project and it's still subject to claims and variations. So hopefully that gives you the starting point where we're coming from. And we're going to primarily focus on this concept of investigation tests carried out prior to the main contract. So let me just, hopefully my screen is live. Right, so the way I've structured this presentation, as I always do, is really start off with some very brief fundamentals. And that's really looking at defining terminology, because we're from different parts of the world, and looking at the basic concept of what a grouted anchor is. Then I'll give a brief description of the project. I'll talk about the investigation tests, the scope, the objectives, and the results of those tests. And really then move on to showing how the results of that testing was used to optimize the design of the anchor itself. And from optimizing the design of the anchor, how we reduce the costs incurred in the waterproof grouting, which is a concept I'll explain later on. We'll then finish everything off with some closing remarks. So that's the basic structure of how the talk is going to be taking place. So, some fundamentals. Most of us will know this already, but I'm not going to assume anything. This figure is taken from the execution code EN 1537, which is part of the suite of Eurocodes that we use. Typically, I'm going to be talking about the anchor head, which is a part of the anchor that usually you can see, not in every case, because sometimes they're buried, but usually you can see the anchor head, and that's a part of the anchor that's attached to the structure itself. I'm going to be referring to the free anchor length, which is a part of the anchor which connects the head and transfers loads from the anchor head through the ground to the fixed anchor, which is fully bonded to the ground. The free anchor length is actually decoupled from the surrounding grout. Now, it's that fixed anchor which is of particular interest to this talk, because That's a part of the design that the initial testing allowed us to optimize, make a lot shorter than originally envisaged, and that resulted in substantial cost savings in terms of the waterproof grouting and other concepts that I'll talk about later on. So moving on to the basic concept now. At the lower end of the scale, we've all heard of rock bolts, which is a particular form of anchor in that it does have a head, a free length, and a fixed length in certain types of rock bolts, typically 6 meters long with working loads of up to 10 tons or 100 kilonewtons. And that's the lower end of the scale. At the other end of the scale, we have the dam stabilization anchors. And in any water retaining structure, the objective is to drill as few holes in that structure as possible. And that's why anchors in dams got very, very big. And typically we can go up to 130 meters long with working loads of up to 17,000 kilonewtons. So these are massive systems. And it's really this part of the scale of anchor technology that I'm going to be focusing on primarily today. So we're going to be talking about the raising of Hazelmere Dam. Now, this dam is located on the east coast of South Africa, near the city of Durban. Here you have Pretoria, Johannesburg, Cape Town, Port Elizabeth, all the main sort of key areas that most of us will know about already, but we're located on the east coast near Durban. The dam itself is located on the Umhloti River in the KwaZulu-Natal region of South Africa, about 5 kilometers from the town of Verulam. It's a conventional concrete gravity dam and it's completed in 1976. Key dimensions that the dam is 478 meters long and 47 meters high. Certainly not a massive dam by world standards, but in terms of the particular location, it was logistically a very, very important structure. More importantly, the dam was going to be raised by an unprecedented 7 meters, something that has never been taken on in this region of South Africa. Now, I've chosen this drone shot, which is looking upstream of the dam, and it shows it in its original state before any work was done on it. And I want you to focus on this particular shot because as I go through the presentation, I'm going to show you progressively how the work's developed by referring back to shots taken from this angle, so you can get a sense of perspective. So key features of the construction work that was carried out for this raising. The first part of things is that investigations prior to the works had showed that the grout curtain had been compromised beneath the dam. And for those of you who don't know, the grout curtain is a wall of grout constructed beneath the superstructure of the dam, and it prevents percolation of water from the storage reservoir through, which can undermine the stability of the structure. So that grout curtain had to be restored, and that was one feature of the construction. The second feature of the construction was the construction of what we call a piano key weir, PKW. And it's a special configuration that is constructed in the spillway of the tunnel and allows us to not use things like radial gates, which are high maintenance items. This particular configuration increases the hydraulic efficiency of the spillway, and in fact increases the effective length of the spillway by a factor of 6. What happened was, even though the dam was going to be increased in height by 7 meters, we had to demolish 3 meters of the original spillway in order to construct this PKW. So by making the overall PKW 10 meters, it actually became the highest PKW ever constructed in the world. So that's something to note. And finally, the third part of the construction was the installation of the rock anchors for overall stability to prevent sliding and overturning of the dam. I mentioned at the outset, 83 ultra high capacity anchors were installed with test loads of up to 19,000 kilonewtons. This equals the highest capacity ever installed. The drill holes were typically 355 millimeters and the overall length about 90 meters. So these are substantially large systems, equaling the largest in the world. And even though we're working in South Africa, the design engineers opted to use a British standard code of practice, BS 8081 1989, to govern the design, construction, and testing of the anchors. That code of practice has since been updated to a 2015 version. So, a brief comment on the site geology. The dam is founded on a material called jointed quartzitic sandstone. And all I'm illustrating here is some core recoveries, which shows the classification of the underlying stratum in terms of a fractured zone and what we termed a more competent zone. But the important thing here is that this is a banded stratum, and the fixed anchors, the most important part that is going to generate the resistance of the anchors, was actually located in the fractured zone. So we had to do special treatment to those boreholes to make sure that the grout that we're using to generate that resistance actually stayed in the borehole. And I'll come to that later on. So primarily we're focusing on the investigation test program, which amounts to the largest capacity sacrificial test anchor program in the world. This slide, again, I'm taking the drone shot from that angle I referred to earlier on, really shows the dam with the original spillway completely demolished, and they're now starting the construction of the PKW in the spillway location. But what's important here is that we elected to install 4 sacrificial anchors, 3 in the spillway, in the stilling basin, in the spillway location, 1 on the left flank as you're looking downstream, and then a 5th test anchor, which is what we call a dress rehearsal anchor, because it was fully configured like the production anchors straight through the non-overspilled crest of the dam. And the idea of that was so that the contractor, who had never worked in this region before, even though they were experienced, could adequately demonstrate their ability to execute an anchor under the conditions in South Africa. So it was very, very important. So we had 4 sacrificial anchors, and if you zone in, you could probably see them on the blocks there sticking out. And on 4 dress rehearsal anchors, sorry, 4 sacrificial anchors and 1 dress rehearsal anchor. And that's part of this program that the client decided to commit to. Now, these are very large anchors. They're full scale. And because of that, we had to fabricate them adjacent to the dam. Up in the left-hand corner, there's the left flank of the dam itself. So we had to fabricate these tendons in a very close proximity and then transport them to the installation location. The test anchors comprise 61 strands. Now, this would be challenging work for production anchors, but 61 strands was the option used to carry out these test anchors, and 4 of them were used sacrificially. Now, one of the issues that is often overlooked, one of the aspects that are often overlooked, when you're putting in a sacrificial anchor and you're looking to test it to its ultimate capacity, which is what we tried to do, you have to isolate the bond zone of that anchor. Now, often this is overlooked, surprisingly, but what we don't want to do in situations like this is have the free length grout contribute to the resistance we're getting from the anchor, because that wouldn't give a realistic analysis later on when we're looking to back analyze what our ultimate bond stresses are that we can rely on design. So what we elected to do is construct what we call an isolator or soft pack at the top of the bond length. And this polystyrene member was specially engineered, placed at the top of the bond length, so that when we stress the anchor, there's no contribution from the free length grout above it. So that when we get an ultimate condition or a maximum load, we know that it's the only thing generating that resistance is the bond length itself. So we can calculate that accurately. Here we have just a few images showing the drilling of the anchors in the stilling basin. For logistical reasons, it made sense to drill the anchors and install them, drill the boreholes first, and then place the thrust blocks over the case boreholes. we're dealing with large loads here, and the idea is you don't want punching forces going into the ground and complicating your subsequent analysis. So we had these 3 meter square thrust blocks actually constructed separately and then subsequently placed over the anchors. This is just a view of the tendon, fully fabricated here and wheeled into the test location on these special bogies. And then subsequently a tower crane lifting the test anchors into place. Remember, these are not production anchors. They're all sacrificial, but the client committed to this level of testing because they understood the benefits that will be derived from it. And once fully installed and grouted, the anchor was supported by a special test frame, left so the grout can gain full mechanical properties and then subjected to testing afterwards. Now, the testing process was quite interesting and very conventional, but what wasn't conventional is that we used a special software to allow us to analyze in real time the behavior of the anchors. And we use a software called Anchor Test, which was a cloud-based software based on iPad, which was very convenient because you don't really want to take laptops into a construction site because it's not terribly robust. But an iPad worked very well in these situations, and we're in real time able to analyze the behavior of the anchors. Essentially, in this software, we're able to input the basic characteristics, 61 strands, the free lengths, the bond lengths, the characteristics of that. Once the software understands that, and then we can now generate our load extension behavior. And in the case of BSA 281, it requires you to take an investigation test anchor through 8 cycles of loading and unloading until you reach an ultimate condition. And that's what we actually generated here. The software, as I said, was very successful and allowed authorized third parties to scrutinize the data, even though they weren't on site, because all the data was digitized and sent to the cloud for storage. It's a very, very useful tool in this test program. Now, I'm not going to delve into the numbers in massive detail, but this is just a summary of the back-analyzed bond stresses that we generated from the site. The important thing to extract from this is that prior to this, the the specialist anchor contractor had not conducted investigation tests of this type before. They would simply rely on a desk study exercise, looking at the geotechnical parameters of the ground and estimate and calculate their bond lengths almost theoretically from that. So in actual fact, the theoretical bond lengths they calculated were up to 67% longer than the ones generated from these tests. And that's very significant because for the bond lengths generated were 6 meters, 7 meters, 8 meters, and 9 meters for the 49 strand, 61 strand, 80 strand, and 91 strand anchors respectively. So for the 91 strand anchors, it was unheard of that you could have bond lengths of just 9 meters when you're dealing with this type of loading. But the important thing here is that we carried out in situ testing on live full-scale anchors, which demonstrated the competence or the geotechnical capacity of the ground. So we could confidently use these values in our subsequent design. And that's what we did. So in addition to the sacrificial anchors I mentioned before, and I showed you a little red circle around it on the non-overspill crest, we also executed a dress rehearsal anchor. And the idea of this was that the contractor had to fully fabricate a full-scale production anchor with full corrosion protection around it, install it so we could critique his technique. We could iron out any issues, and this proved to be very, very, very useful. So this is a photograph showing this large anchor being winched into position along these bogies to its installation position on the crest of the dam. Remember, this is still a test anchor, and I put a little circle on there showing me inspecting that anchor while it's traveling to its location. Now, in order to home these into the boreholes, drilled through the dam and into the underlying rock, you have to use special equipment. And this is what we call a dinosaur, which is a special rig with large pulleys on it. And it allows you to winch the tendon, which weighs a lot, into position and then safely lower it into its borehole within the dam and within the underlying rock. The stressing and testing is an important part of this exercise. And because the code of practice we used demanded that the anchors have to be cyclically loaded, we had to commission the world's largest hydraulic anchor stressing jack. And this was manufactured in Germany. I'm out of the three gentlemen there, I'm the one in the middle. And the gentleman on my left-hand side is actually 6'2". So it gives you a feeling for how big this jack is. Essentially 22 meganewton capacity. That's 4,946 kips with a stroke of 1,000 millimeters. So this is the largest stressing jack ever commissioned for anchor technology that we know about. It was necessary because these anchors had to be cyclically loaded, and because of the size of the length of the free lengths, we had to have sufficient travel in that jack to facilitate the cyclic loading. Again, using anchor test software, we're able to subject this special dress rehearsal anchor, because it's not an ultimate test anchor now, it's installed in position, and we're subjecting it to what we call a suitability test, or in American speak, in US speak, what you would call a performance test, where simply we're subjecting it to 3 cycles of loading, extended observation periods, a little bit more rigorous than what you would call your proof test or our acceptance tests, a little bit more rigorous to show that the anchor's performing adequately. In this particular case, we also looked at what we call the apparent free length calculation, which is automatically generated in the software. And this really demonstrates that the anchor is acting elastically and that the load is transferred from the anchor head right through the ground adequately to the fixed anchor zone without any load caught up in friction in the free length, which typically can happen with long anchors. One thing I would say also is that provision was made in this system that if this anchor, dress rehearsal anchor, didn't perform adequately, then we had an adjacent position next to it to install a production anchor once all issues were ironed out. Luckily, in this case, it wasn't needed because it would perform satisfactorily. Now, the dress rehearsal anchor, as I said, it's not a sacrificial anchor where you don't need corrosion protection around it because the loads are very short term. We had to install a full corrosion protection system around this. Now, this is done by applying a corrugated plastic duct around the anchor tendon. And in BSA 281, you're permitted for permanent anchors to apply something called single protection or double protection. Both systems are valid in BSA, in UK practice, in European practice. However, if you're applying a single protection, then you're required to test that protection in situ to guarantee that that protection has its full integrity. And that's what we had to do on this project. So once that protection system was installed, we had to water test it to show that there were no breaches in it. Then we installed the tendon inside it, water test it again. And once it satisfactorily passes a water test, we are comforted that the full integrity of that system is in place and the single protection is satisfactory. With double protection, you don't need to do that. Now, we know historically that with anchors, the anchor head is the most vulnerable position for durability issues. And the majority of corrosion failures historically have occurred at the anchor head. So special provisions had to take place with this dress rehearsal anchor to ensure that the anchor head was adequately protected. Here, once the tendons are chopped off, this is 61 strands here, they were chopped off, the whole thing was then injected beneath the head, first of all, with a special wax, corrosion inhibiting wax. And this was subsequently placed around the chopped tendon elements so we can adequately protect them as well. Once that wax has gone off, the whole thing is encased in a galvanized cap, which is removable, so it can allow subsequent inspections of the anchor head during its service life. So this is the extent we had to go to ensure that the anchor heads were adequately protected, particularly because it's a very vulnerable zone of the whole anchor system. So how are cost savings affected by this initial testing? Well, one of the main features when you're dealing with this type of ground is that you have to waterproof the boreholes or grout-proof the boreholes. You have to ensure that the grout you place doesn't get washed out through fissures in the ground. So just refer you to this little schematic here to show you how the layout of everything is. We have the dam itself, the dam wall and the reservoir of water illustrated schematically. We have the borehole and the anchor tendon installed inside it. The phreatic surface, which is a natural water-bearing surface in there. And then the founding stratum, where the fixed anchor zone is located. And it's that founding stratum that we have to ensure that the grout is not washed out. So you can adequately retain mechanical properties of that grout when you're looking to stress it. So just cast your eyes on the diagram on the right-hand side, which is a schematic representation of the borehole. Now the arrows show that there's a passage of water which can freely flow through the fissures and partings in the rock. And that can undermine the placement of primary grout. So if we simply placed our tendon in the borehole like that and grouted it up, then if we didn't do anything to ensure that that borehole was grout tight, then water could pass through, wash away some of that grout and undermine its integrity. So when we come to stress it, either the anchor tendon would start creeping excessively or simply pull out, which wouldn't be satisfactory. So what we have to do is waterproof that borehole by placing a grout initially in the borehole, re-drilling that, water testing it to ensure that it has it passes the criteria that are imposed. And if it passes that criteria, we can then safely place our tendon in that waterproof borehole, grout it up, knowing that the grout will actually stay in place. So we can stress it and it can give us the resistance that we desire. And what that essentially does is satisfy the condition in BSA 281, which is that the grouting is also to seal the ground immediately adjacent to the fixed anchor in order to limit the loss of grout. Very, very important. And because we carried out testing beforehand and optimized the size of those fixed anchors, we're able to ensure that they could be safely designed much shorter than anticipated, which limited the amount of pre-grouting we had to do and waterproof grouting. Now, in order to effectively waterproof a borehole, you sometimes have to go through several cycles of pre-grouting, re-drilling, water testing, etc. Several cycles to get that right, so you can pass your permeability criteria. So by shortening the boreholes and making sure that they can safely be shortened, the client saved tremendous amount of money on this particular aspect. So it's worth bearing in mind. And that was one of the benefits of the pre-production anchor testing. This is a down the hole camera which we placed, and it shows the effectiveness of the waterproof grouting, where on the left-hand side, you're seeing fissures, these round circles of fissures that are being grouted up and exposed after re-drilling and reaming out. And on the right-hand side, you're seeing the interface between the dam concrete structure and the underlying rock, and that interface is also grouted up. If that pre-grout wasn't in place, then the primary grout would simply just flow out and we'd lose the mechanical resistance we desire. So it shows the effectiveness of the pre-grouting program in filling all the voids. So the status of the anchors. I'm happy to say that before the contract was stopped, as I mentioned earlier in the introduction, in 2018, we had locked off 73 of the anchors, and these comprise 91, 80, 61, and 49 strand tendons. All of these were stressed and tested, and all of them successfully demonstrated conformance with BSA 281 1989, which meant there were no failures. So that pre-testing program that we did, the optimization of the fixed anchor zones, even though they were shorter than what was theoretically predicted, satisfied the criteria and there were no failures. So that the testing program was effective and the in situ values that we used. In terms of the structure itself, I've picked views of the structure, typically looking upstream, as I mentioned before, so you can see the PKW in its finished form, as it were. But remember, we still have 10 anchors to stress, test, and instrument with load cells. And if you're very sharp-eyed, I'm not sure if you can see my cursor moving, but these are the tendons of some of those remaining anchors still sticking out pending the stressing and testing program to come. Another view of the drone as we flew the drone over, look an aerial view looking down at the PKW, which is a very simple configuration, but as I said, it increases the effective spillway length by a factor of 6 by adopting this configuration. And it's a low maintenance solution because it doesn't allow you don't need radial gates to control the flow using this configuration. And again, now looking downstream, these are just views of the dam looking downstream, beautiful area, but it shows the drama of the PKW in this view. So to some closing remarks. First of all, I'll say that the Hazelmere Dam has presented South Africa with a number of important world firsts. The first is that the largest capacity cyclically loaded anchors were installed. The capacity equaled the highest ever installed, but these are the largest capacity cyclically loaded anchors ever installed in the world. It's also saw the use of the largest capacity stressing equipment for anchors. And I showed you the photograph of the large bespoke stressing jack, 22 meganewton capacity. The highest PKW at 10 meters ever installed. The largest capacity sacrificial anchor program, and the first use of the real-time monitoring software anchor test on a dam for the storage of data and the real-time analysis of the performance of the anchors. So a number of world firsts that South Africa could be proud of. And I could add to that list by saying that we're also going to be introducing the largest capacity hydraulic pressure transducer annular load cells ever installed on an anchor as well. The second remark I'd like to make is that the project demonstrated the importance of implementing full-scale anchor trials for the optimization of the fixed anchor and the substantial cost savings that were generated from that in terms of reducing the amount of waterproof grouting that was actually employed on the project. I will also say that the waterproof grouting was effective in that the anchors installed satisfied the acceptance and suitability tests, or in US speak, performance and proof testing that was carried out. And finally, the use of the innovative data management software anchor test proved very, very effective in assessing the anchor performance with respect to the acceptance criteria stipulated in BSA 281, 1989. And with that, I'd like to thank you for your attention.